An example of shell balance, using the example problem you can see here. I'll leave it up just so you can read it and think about it. Okay, let's start. To start, we have to define our axis, and so we have our positive axis going to the left and down. The problem statement tells us that the flow goes down and comes out of the bottom. To draw like a two-dimensional figure, when you have your delta x and your delta c going down, then you have your pressure going to the top, to the bottom. I'll discuss how I chose my PO and PL to be one going down, one going up. Then you also have your shear stresses as well as a gravity force. We're going to start with the pressure balance. As you can see in my notes right here, I chose PO to be on the top because for flow to go down, the way it was defined in the problem, high pressure to low pressure. Like the pressure, we always write it on like as in going into the control volume. In this case, it would be positive because we define our axis to be positive down, and then our PL is negative because it's going up, and in this case, that's our negative C direction. So for pressure balance, we force balance with the pressures because at the end we want to like do a balance of pressures. So we know that we can equal a force if we multiply pressure times area. So simply we start with PL. PL, as we just said, is negative. Negative times the area. That's just simply the area of that the pressure is exerted. In this case, delta X and delta Y. And that's in your C plus delta C. So you start here, your axis is going down. So you start at C and then you add a little difference and you end up in plus C, and that's why you end in P, like in the line of PL. And you do the same thing for PO. So that's simply the pressure. Now we move into the shear stress balance. For the shear stress balance, it's the same thing. We have to multiply the shear strength of the area to equal a force. XC is positive in a positive surface. So like the shear stress is positive in a positive surface. What that means, like this, usually if you see it like this, you could see that the top of our square would be right here. Therefore, that's why our shear stress going down, in this case, is positive. The negative surface, which is at the bottom of our axis, and this case is going up, and it's a negative shear force. We start with the x delta x, which is right here, and that's our positive shear force. So we have a positive sign right here. We multiply by area, in this case delta c and delta y. Same thing for the other one, and this time we have a negative. So that's basically it. And then for our last force balance, we have gravity force. In this case, we know the definition of F equals mg. You could get m by rho times volume times gravity. We ended up with P delta x, delta c, delta y, which you can see that's the volume for a little cube. We have to add all the forces together. So we ended up, that's just whatever I just did, combine. Then, after we have that, we divide everything by delta V. Delta V is defined by delta X, delta Y times delta C. After you do that, you go back to your calculus definition. You take the limit as delta C goes to 0, and then you get a dp dc, which is a negative direction, because your ending point is negative and your starting point is positive, so you have a negative change. And the shear stress balance, we have a positive change because you have your final is bigger than your initial, and then you have simply rho g because we divided by volume. By definition, dp dc d tau dx plus rho g. We know that our change in pressure is from PO to minus PL over L, because they told us that delta C equals to L. But we don't know the tau dx. That's what we're solving for. So we simply integrate at x is 0, or shear stress is at a minimum, and at x we just have a variable, a placeholder. So we simply for that, as you can see, that's the answer is for the problem. If you guys have any questions, feel free to post.